Okay, so I'm solving problem 1793, general plane motion. And what do we have? We have a cylinder bar. It's 12 kilogram and 3 meter long, and it slides with one end along a horizontal floor and with the other end along a vertical wall. These are smooth surfaces, negligible friction. It says angle for the position is 60 degrees. We're all told that angular velocity is 2 radians per second, and we need to find so omega 2 radians per second given angular velocity. Angular acceleration, we need to find it, as well as the reactions at A and B. I have here a drawing for the problem, and the motion is in vertical plane, so we have weight that's causing the sliding of the bar. We're told that, and it's expected that omega is clockwise. Omega. And then we're having just normal reactions at A and B. So this is point, we use A and B. So we have normal force at A and normal force at B. Okay. A reference frame would be X to the right, Y up could be along the wall, Y. It means that omega is a negative value, and expected for alpha to be in the same direction, also negative. So this problem is a good candidate for solving it using instant center. Instant center, it's the if you complete a rectangle, is the corner of the rectangle at the opposing to this corner here. How do we know that? The velocity of A is, and we can even calculate these velocities, although they're not needed. So velocity of A, it's along the floor, and so velocity of A, and velocity of B, it's along the wall, down. Okay. What else I have on the figure? So if the length is given 3 meters, and we know the angle 60 degrees, we can calculate this length, and we can calculate this length using trigonometry. And I said that the moment equation of motion, it's good to write it in this form, equation 1719. So equation 1719. Why? Because if we sum moments about the instant center, the moment of the normal force A and the moment of normal force B, they're both going to be 0 because the line passed through instant center. So it'll be just the weight that is causing moment. So it will be a simplifying, what are the decouples the moment equations from the force equations. We'll have to write force equations at some point because we need to find the reactions in A and in B. But if we're to just find alpha, the angular acceleration, then this equation would be enough. Okay, so let's take the equation of motion. Sum of moment, 17.9. So sum of moments about the instant center is mass moment of inertia of the bar about the instant center times alpha. Okay, so let's calculate. Well, I can expand this. We'll calculate below the mass moment of inertia about the instant center using parallax theorem. So what do we have? We have, let's assume positive. It will be counterclockwise. So I'm going to have, and we don't know alpha, whether it's one way or the other, so let's just leave alpha as is. So I have the moment of the weight only is generating a negative moment, so it's going to be mass times accelerated gravity, and the arm of the weight, it's half of this distance, so it'll be times 1.5 over 2, and then this is equal to, we said, I about instant center times alpha. So let's find I about the instant center. I said that we're using parallax theorem, so it's going to be I centroidal plus distance. If this was, let's use G. So it will be mass of the bar times distance from the point to the centroid squared. So IC G squared. I have IG calculated plus mass is 12 times this distance, it's half of the bar length. So it'll be 1 over, 3 divided by 2, and this goes squared. Okay, so let's see what we have. We have 3 over 2 is 1.5 squared times 12 plus 9 equals 36 kilogram meters squared. So we can now calculate alpha from this equation. So I have alpha equals negative, negative meaning that it will be a clockwise angular acceleration. So it's negative, mass is 12 times 9.81 times 0.75 over the 36 kilogram meters squared. And so let's see what we have. I take 36 inverse times 12 times 9.81 times 0.75 equals, that's 2.4525 radians per second. Answer. So we solved part 1 of the problem, but it's not enough. We need to find reactions that support it. To find reactions that support, we need to use the force equations. That is Newton's second law, written along the x and y axis. So what do we have? We have sum of forces in the x direction equals mass times the acceleration of the center of mass in the x direction. And sum of forces in the, I said force, I wrote moment, sum of forces in the y direction equals mass times acceleration of the center of mass in the y direction. Okay? So for the first equation in the x direction, I have negative, positive will be to the right, negative nb, and that's it, equals mass times acceleration of center mass in the x direction. And for the vertical direction, I have na minus w, that's mass times acceleration of gravity, equals mass times acceleration of center mass in the y direction. Okay, these are the two equations, but we don't know the accelerations in the x and y direction of the center of mass. We're going to state the relative acceleration equations that we learned earlier. So it will be acceleration of the center of mass, the vector equation. Acceleration of the center of mass vector equals, and I'm going to write it about both points A and B, of, so G, acceleration of G, because I need the x and y components of it, relative to A and relative to B. So starting with point A, I said acceleration of vector of G is acceleration vector of point A, and then is alpha, which we have it, vector crossed with the position vector of G with respect to A. So it will be vector AG, starts at A, ends at G, and then I have negative omega squared multiplied by the same AG vector. Okay? So this is the scalar, or the I and J components of it. We'll go acceleration of G in the x direction times I plus acceleration of G in the y direction times J, this is the left-hand side, equals, we're looking at acceleration of A, there's nothing in the y direction, so it'll be just acceleration of A in the x direction times I, 0 in the y direction, and then I move forward, and we have, so we'll have a cross product alpha, and we have a value for it. It's negative. Should have put the minus here. It's essential to have a minus. So let's use it with its sign because it's negative of k. So we have the negative 2.4525 times k crossed with, and the vector ag, if you look at the vector, it projects positive on both x and y. So in the x direction, it has 0.75 meters, half of this length. So, and this is I, plus half of the vertical piece will be the y projection. So I have 2.598 divided by 2. That's 1.2945 J. And we've seen this before. It's so when you do this cross product, you get negative magnitude of what's along K times the J component. So I'll have negative, it's positive 2.4525 times 1.2945, and this is I. And then I have plus what's along K times the x-axis component. So it will be plus, but with the minus in front makes minus 2.4525 times 0.75, and this is the J. Alright, so I've got this. We used it in class before. I have it written here. You know, expanding, using the determinant, expanding the cross product. So negative, well, here I have with omega, but it could be alpha as well. So negative, and the y component positive, and the x component for J. So that's what I just did. Okay, so this is what the answer of this multiplication is. So let's continue. I have alpha times AG, and it will be the positive, and I need to multiply 2.4525 times 1.2945 equals, so 3.1748, and this is I, and then I have negative, and multiplying 2.4525 by 0.75, this is negative 1.8394 J. Okay, and then I have the the last term, that's omega squared, and omega is, so it will be 2 squared. Omega is 2 radians per second. So I have 4 times 0.75. Again, vector AG has the same, it's this one. So this is a constant multiplying a vector. So I have negative 4 times, so 4 times 0.75, that's 3 negative in the I direction, and I have negative 4 times 1.2945 equals negative 5.178 J. I need to, if we separate these over x and y, or I and j, so we're having the j terms, all right, and that scalar equation along the j, along the y-axis, has just so by the way, how many unknowns we have here? We have 3 unknowns, but we can solve for 1 because the the j equation is decoupled from the y equation. Okay, this is the only reason. So I'm going to say acceleration of g in the y direction, point G, equals these 2 terms. So it's negative 1.8394, negative 5.178. Okay, I still have this one, so plus 1.8394 equals, that's negative 7.0174 meters per second. So I have the acceleration, and I can solve for now going back to, so let's say this is equation, I go to equation 1 star and equation 2 stars. So with this one taken to equation 2 stars, it gets me normal reaction at A is mg, move to the other side, mg, that's 12 times 9.81, plus mass is 12 times the acceleration we just calculated, negative 7.0174. Okay, so this one is, I said 12 times, I can put 12 in front, so it'll be 9.81 minus 7.0174 equals times 12 equals, it's 33.5 newtons is the answer. Okay, so we've got Na. To get the other normal force, we need to repeat this approach for acceleration of g relative to point B. It is also possible to write sum of moments about the centroid, okay? And we know already alpha, so we could solve for NB. All right, so that's another possibility. Let's go the same path. Practice a little bit more the kinematics of rigid body. So I say now acceleration of g vector is acceleration of b plus alpha vector crossed with the position vectors from b to g, so b to g, negative omega squared times bg. All right, here we're going to see a cross product. So alpha is negative 2.4525, and then times k, and then bg has the same projects the same magnitude, but both are negative, so it will be crossed with negative 0.75 I and projects with negative 1.2945 j. Okay, so there will be the same results. It was just that the signs will be flipped. So this becomes negative, this becomes positive. All right, so let's see. What do we have? We have acceleration of g in the x direction times I plus acceleration of g in the y direction times j. It will be this one, same as before, equals. And now I have acceleration of point B. So acceleration of B is 0 in the x direction, and it has a non-zero value in the y direction. So that's acceleration of B in the y direction times j. And continue. We'll have, I said that what was here, this sequence coming from the cross product, is going to be with flipped sign. So it'll be negative 3.1748 I, and was negative now becomes positive 1.8394 j. Okay, and then I have the omega squared times ag, and same story. So I have ag is negative b g. So this sequence, I'm going to flip signs. So it'll be plus 3i plus 5.178 j. Useful equation here, although useful equation here, you could start with either relative motion about b or relative motion about a. So useful equation this time is the one along the I-axis, because the point B has no acceleration along that axis. So I'm going to collect this term with this term and with this term. It allows me to calculate the unknown acceleration of g with respect to x. Acceleration of g with respect to x is going to be negative 3.1748 plus 3, and that's about it. So this is equal to negative. So I have negative 0.1748 meters per second squared. Okay? So with this one now, I take it to, let's take the bar off. So I take it to equation 1 star above, and I can say NB equals negative, remember there's a minus in front, so I multiply by minus 1, negative m, or flip term, so negative m, that's 12 times the acceleration that we just calculated, negative 0.1748 meters per second square. And so what's the answer? 12 will be a positive value. 12 times 0.1748 equals, it's 2.097, 2.1, let's say, newtons. Okay, so this was it. Had to make use of kinematics, and this being said, I stop recording. Let's see, is it centered? You can take a screenshot before I scan this to PDF and post it for you. Alright, thanks for watching. Okay, so I'm going to solve problem 17102. It is about a slender rod. It's guided with point A and A along a quarter circular path, and B, it slides on the ground horizontally. There's friction at B. Coefficient of friction is 0.4. And then we have the length of the bar and the weight, 25-pound weight and 6 foot long. The circular path is 3 square root of 2 foot radius. Okay, it starts from rest when theta is 30 degrees, and we need to calculate alpha, the angular acceleration for this instance. Okay, I have already represented in red the normal force at A. That will be, since it's frictionless, has the direction of the center of the quarter circular guide. And then B, we have the normal force, and then we have the friction force. There is an arrow indicating direction of motion, so friction opposes displacement at B. And this is about it. So, one more thing. We may or may not use it. Theta dot is going to be omega of the bar AB, and theta double dot is going to be alpha of the bar. Okay, so I drew the figure here, trying to have it at scale. Summary of what's given, the lengths and the bar length and radius and angle, theta dot, which is omega at 0, alpha unknown. Friction force, since it's motion, we have kinetic coefficient of friction times 0.4, which is given times normal B, and the normal force. I did some calculations using geometric calculations. So we have a right angle triangle. I drew the perpendicular from A on the x-axis. Center of the guide is origin. And this is point C. I named this point D. Center mass of the bar G. O is the origin of X, Y. Okay, so using the angle, 30-degree angle, we can calculate AC and we can calculate BC. AC is going to be 6 sine of 30 degrees, and it's 3 feet. BC is length of the bar cosine of 30 degrees. That's square root of 3 over 3. And then we can calculate the distance from O to C. Distance O to C is going to be the radius OA, that's square root of 3 over 2, squared minus AC, which we calculate to be 3, and OC ends up being 3 feet, which means that this it's a right angle triangle OCA. It's isosceles, and the angle is 45 degrees here and 45 here. It means that the normal force at the guide, which has the direction of the radius, it's 45 degrees from the horizontal. Okay, so if I extend this, clearly this angle is this angle, it's 45, but together are 90, so 45 and 45, okay? There's also the weight acting at the center of mass, which is half between A and B. And we're ready to write the equations for this problem. So we have 4 unknowns. There's the normal force at A. There is normal force at B, I said 4. And then, friction force, we stated it's normal at B times friction coefficient. We're going to see the acceleration of the center of mass over X and Y occurring. So we need to use, in addition to geometry, we need to use some kinematic equations. Okay, looking at the, all right, so equation of motion, general plane motion. Sum of force over X, sum of force over Y equals mass times acceleration of the center mass into X and Y respectively. And then we have options, some moments about the centroid, the center mass, about a point, P, or about the instant center. So let's start with the instant center. Instant center is going to, I have the velocity of A is tangent to the path. The normal to the path is from A through O extended because it's going to be perpendicular to the velocity. And then I'm drawing the line that's perpendicular to the direction of sliding of B. The velocity will be along horizontal. And where the two intersect, there's the center. I'm drawing here quickly the velocity or the vector tangent to the path at A. So summing moments about instant center will make the moment of the normal force at A 0 will make the moment of the normal force at B 0, but not, unfortunately, we have friction. So without friction would have been ideal situation, and just writing sum of moments equations would have been enough to calculate alpha. Okay, and that of course would have need to, if we use the instant center as the point, reduction point for moments, we need to calculate the distance from G to the instant center to apply parallel axis theorem. The other option is to sum moments about point B. Normal at B and friction force will have so it's going to be 0 moment, the n at B and friction force. Normal at A does not have, it's not through B, it's through O, so it occurs as an unknown. And then we have we could sum moments about point O, and NA will have no moment, but I'm going to see a moment for NB. And still we need to calculate the distance from O to G. So let's go with the first set of equations, because there's no benefit of doing it otherwise. So we're summing forces over X and Y and some moments about the centroid. Okay. All right. So sum of forces in the X direction equals mass times acceleration of G in the X direction. Okay, and this is, so forces in the X, I have the friction force, that's nu B NB, and then I have the negative, positive will be to the right, I have negative NA cosine of 45, so it would be NA, and cosine of 45 equals sine of 45 square root of 2 over 2, all right, and then this equals to the mass of the rod, that's W over G, acceleration to gravity, W over G, times the acceleration of the center of mass in the X direction. Sum of forces in the Y direction equals mass times acceleration of G in the Y direction. Okay, and here we have, so it will be NB positive up, and then I have negative W, and then I have NA sine of 45, if we're looking at this angle, over the other is 45, so and this will be again square root of 2 over 2, equals weight over G, that's mass in slugs, times acceleration of G in the Y direction. And then sum of moments. Now, sum of moments about point O equals centroidal moment of inertia of the bar times alpha. And so let's see. We have, and we're going to assume positive to be counterclockwise. It's best not to break with this rule because alpha is positive when it's counterclockwise. And if we do any kinematics where we need to multiply alpha, cross product of alpha with some position vector, that's, we need to take care of changing to minus if alpha is assumed positive clockwise. Okay, so the moment of NA. So I have the horizontal force is creating a positive moment. So I have NA square root of 2 over 2. That's the horizontal, and generates a counterclockwise, that is positive moment. And the arm of the force, it's going to be the distance AC, which is 3, minus the distance from G to the horizontal. Okay, so this is going to be 1.5. All right, so I have, or is it? So let's double check. We're having so this piece over this piece, it's going to be 1 over 2. So we have similar triangles, and this over this is also this over this. So I have G and never name this, so I can call it E. So GE over AC is going to be 3 over 6, that is 1 over 2. And AC is 3, so GE is going to be AC over 2, that's 1.5 feet. Subtracted from 3, it's 1.5. So I'm going to say times 1.5. Okay, so that was 1. And then I have the moment of the vertical component of NA, and that's going to, the arm of it's creating a negative moment, and clockwise rotation, and the arm is going to be OC. So I have NA square root of 2 over 2, that's the vertical component, and then OC we calculated is 3 feet, okay? And then we have the negative moment of W, so negative moment of W, and the arm of the arm of the moment it's the distance from O to E, and the distance from O to E is BE minus BO. BO, we have it calculated. BE is going to be half of BC. So half of BC, it's 3 square root of 3, square root of 3 over 2. So that's half of BC minus BO or OB. This is negative, well, we have it here, 3 square root of 3 minus 3. 3 square root of 3 minus 3, that's minus minus, so it'll be plus 3, okay? And this is equal to, we've been here before, so mass moment of inertia about the centroid of a slender rod is going to be 1 over 12 mass times length squared, so that's going to be weight of the bar divided by G times length is, well, I have weight, I use weight, but this is known. Well, we'll need to go through one more time these equations and fill in everything that's known. So 0.4 will be here. This is 25 pounds, 25 over 32.2, okay. All right, so I said W over G times distance AB squared. That's right, AB squared over 12. Okay, you go to the back of the book, and we have a rod, and about the either x or y axis, it's 1 over 12 ml squared. So we have 3 equations, and we have how many unknowns other than NA and B and alpha? We have, well, which we never multiplied with, sorry. We have AGX and AGY. We need to relate AGX and AGY to alpha. So we need, and that means, so one more time, I have NA and B unknowns, 2 more, and so 4 or 5. I need to add 2 more scalar equations in order to solve this problem. Okay, and that will come from kinematics. That means it's a matter of relating alpha to the acceleration in the x and y direction of the center of mass, and we need to make use of the fact that point A, it's moving on a circle, and point B is moving on a horizontal line. The way of doing it is to state the relative acceleration equation, vector form. Acceleration of B is acceleration of A plus acceleration of B with respect to A, and acceleration of B with respect to A is going to be alpha vector crossed with, so we have B with respect to A, so it's going to be vector AB, that's cross multiplied with alpha, and then I have negative omega squared times AB vector. All right, so this is 1. I have omega equals 0, so this part luckily goes to 0. So And then for acceleration of A, I need to recognize the acceleration of A is that of a point that's moving on a circle. So let's see, I can say acceleration of B, and it's only in the x direction. In the y direction is 0, there's no motion in the y direction, I, and then plus acceleration of point A, and that's only acceleration of A is acceleration, so acceleration of A is the tangential acceleration of A only. And for a point that's moving on a circle, it's, well, we can tell it's x and y components. So I have, if this is 45, this is also going to be 45. So I'm going to say acceleration of A tangential times, we're looking at so in the x direction is positive, square root of 2 over 2, that's a sine of 45-degree angle here. And then this is times I, and then I have plus acceleration of A tangential, square root of 2 over 2, this should be the cosine of 45 degrees, J. So that's A. And then I have alpha times AB. So we had it like negative alpha times the y component of AB. So I have negative alpha times the y component of AB. The y component of AB is this piece AC, which is 3, but negative 3. So I have negative 3 times I. And then I continue plus alpha times the x component of the vector AB, and that's negative distance BC. We have it as negative square root of 3 over times 3. BC negative square root of negative 3 times square root of 3. Square root of 3 J. Okay, and this is it. I could have squeezed everything here. So plus alpha times negative 3 square root of 3 J. Okay, so let's see. We have with this equation, this new equation, what new information we acquired. So really, what we want to do is to state acceleration of B as or of the center of mass as function of alpha. It's what we need to do. So this was one, and we had okay. So if we collect the J terms, there will be this one and this guy here. We can solve for acceleration of T essentially. So acceleration of, so one more time over J. So we have 0, there's no J component to the left, and we are going to see acceleration of A tangential, which is acceleration of A. It's going to be as function of alpha, so let's say this is staying and these two move on the other side, so I'll have alpha, and this was minus plus, but goes to the other side, will be negative alpha times 3, okay. So it was negative, positive, negative again because it moves to the other side, and this one is negative, goes with plus, so it will be plus alpha times 3 square root of 3, and then I divide this by square root of 2 over 2, okay. So acceleration of T, what do we have? We have some alpha, it will be a positive value because this is bigger, so I have alpha times, let's see quickly what everything here is. I'm going to put a fraction number. So 3 square root times 3 minus 3 equals times 2 equals over 3 square root equals. So alpha times 2.5359. foot per second squared. Okay, so we have acceleration of point T, and now we can state, and its direction is at 45 degrees and down, so projects negative over y, positive over x, and then I'm going to say, so this was 1, I'm going to say acceleration of g with respect to a. So acceleration of g, the center of mass, in the x direction I, plus acceleration of g, y projection times j, equals the acceleration of a, which we have it, acceleration of a vector. I can even say what it is. Well, okay, let's say acceleration of a vector. And then I have plus alpha crossed with it's of g with respect to a of vector ag. And then I have negative omega squared times ag, but same as before, this goes to 0. Okay, so I have the right-hand side is acceleration of a, the x projection, and that's alpha. So let's not forget the alpha, this remains unknown, so it's alpha, and then times this piece, multiplied by, it will be, if this is the 45 degree, and it's sine of 45. So I still have it, let's put it in the memory. So this number 2.5359 times square root of 2 over 2. So times 2 square roots over 2 equals, so it's 1.7931532, and this is the I component. And then I have negative, it will be this piece times cosine. So, but it will be sine and cosine 45 the same, so it will be negative alpha times 1.7932j. We took care of this one. And then here we have a cross product. We saw this earlier. The AG vector has same orientation, is going to be half of the AB vector. Okay, so I have this part continues here. So let's see, I have negative alpha times the horizontal projection of AG. That's a negative value, and it's half of BC. So 3 square root of 3 over 2. And there's a minus. Negative 3 square root of 3 over 2. And this is the I. And I have plus alpha times the y projection of AG. The y projection of AG is half of the y projection of AB. So it'll be 1.5, but is negative. Negative 1.5. And this is J. Okay, so I'm looking here, and I'm looking here. So we have acceleration of the center of mass in the x direction. It's taking this component and this component. So it's going to be alpha times 1.7932 minus plus 3 square root of 3 over 2, and then the acceleration of the center mass in the y direction, it's going to take the, okay, the j. So the j now, and there's one here, and there's another one here. So I said alpha comes in front, yes, it's negative 1.7932, and then negative 1.5. 1.5 equals. So this one and this one. So it'll be a negative value. Not surprising. So I have, I erased it, was on the screen. 1.7932 plus 3 square root times 3 over 2 equals, this is 4.3915 1.13 alpha. And this other one will be a negative value, we said, so it's 1.7932 plus 1.5 equals, that's negative 3.2932932 alpha. Okay, so we've got the accelerations of the center of mass. So at this point we have, back to the force and moment equations, we have AG of x becomes alpha with a multiplier, AG of y, alpha with a multiplier, so we have just alpha as unknown, and then we have NA and AB. So really a set of three equations with three unknowns being alpha and NA and NB. Okay, so I said this is 4.3913 times alpha, and this one here is negative 3.2932 times alpha. Okay, all right, so times to flex our algebraic muscles. And so let's see, I'm going to transcribe the set of three equations. So it's 0.4, the first one, 0.4, and b minus 2 squared over 2, that's 0.707 NA, all right, equals, there'll be 25 pounds, the mass of 2, okay, so, and then times 4.3913 equals, and that's a positive number, so 3.4094 alpha. The second equation, I have NB, and then I have NB, okay, NA, we're missing it, so NB minus 0.707 NA, and then I have, could have kept all the unknowns on one side, so negative equals 0, and here I have negative. So what I'm doing, I'm moving W to the side, to the right, and this piece to the left, same as I did earlier. This is equal 0, this will be equal plus W. So it's minus goes to plus 3.29, and I think I copied the wrong number here, sorry. So this is for the x component, I have 4.3913 alpha, and this is positive 3.2932 alpha equals W plus W is 25, okay? And the last equation is the moment equation. So I have NA was square root of 2 over 2707 times 1.5 equals, that's 1.0607 N A minus NA comes in front, so we have let's see, the full thing, so combining the two, again, when we sum moments, we had and do I have everything? I hope I haven't missed. So we said moments about, I said, oh no, it was the center of mass. Moment, let me double check this equation. I saw something that is not looking right. So I have NA, and the arm is 1.5 as a negative. Okay, so that's a positive moment, correct? And then a negative moment, NA square root of 2 over 2 times the arm is 3. And then I have the wow, looks like I wrote, let me pause. All right, I paused because I had some mistakes in the moment equation. some reason I was combining some of moments about B with that of G. And really, it's a better alternative, slightly better, if you sum moments about point B. All you need to do is just take the mass moment of inertia of the rod about point B, and then friction force and NB do not have moments. But I started with sum of moments about G, and I'm continuing. So where was the mistake? I had a moment about weight. Weight does not create a moment if I sum about G. Rather, I have a moment caused by the friction force, and that's a positive moment, counterclockwise. So I have 0.4 times NB, that's the friction force. Arm of the force is going to be this piece, which is half of this, it's 3 over 2, 1.5. And then I have a positive moment, negative rather, caused by NB, clockwise rotation. So it's NB times the arm will be half of this. We calculated BC as being 3 square root of 3. Okay, and that's it, equals to IG times alpha. So IG is W over G, mass and slug, times AB squared, that's 6 foot over 12. Okay, so let's go back and see. So I have for moments, I have NA collects, so NA square root of 2 over 2 minus, so it'll be 1.5 minus 3 is negative 1.5. So it'll be negative square root of 2 over 2, 2 square root over 2 times 1.5 equals, this is a negative value, so negative 1.0607 NB. I'm sorry, not NB, we're still at NA. NA. So I took care of these two, and then I have NB now. There is 0.4 times 1.5 minus 3 square root of 3 over 2. So I have 0.4 times 1.5 equals, and then I have negative 3 times 3 square root over 2 equals. So this is negative 1.998 NB. So an A and B, okay, and this is equal to, or rather, we said that alpha also is going to stay to the left. So I have W over G, that's 25 over 32.2, times AB, that's 6 squared over 12 equals. So this is 2.3292 alpha equals 0. Okay, so we have three linear equations with three unknowns, you can solve it, Kramer's rule or substitution. So one way of doing it, of course, we need to keep alpha as an unknown, so we need to say we can get rid of NB from the second equation, substitute in the first and the third, and then eliminate NA between the two new equations and find alpha. I have the answers here. So alpha is positive 4.01 radians per second squared, and then NA is negative 11.2 pounds, and NB is 9.01 pounds. This is the answer. The book could have asked for the reactions at A and B, but they left it as a byproduct of this problem. Okay, so I'm stopping here. Thanks for watching.